Deep in the cosmic graveyard lie white dwarfs, the dense, Earth-sized remnants of stars that have lived out their fiery lives. Their stellar corpses, cooling slowly across billions of years. But within these quiet cosmic tombs, something unexpected is sometimes detected. Signals, whispers from the stellar afterlife that science hasn't fully accounted for. These aren't the predictable pulses of a pulsar or the familiar glow of a planetary nebula. These are the strange, the puzzling, the truly unexplained signals. They hint at possibilities that stretch from the fringes of exotic physics we barely understand to the mind-bending idea of technologies far beyond our own. It's a realm of cosmic intrigue, a place where the known edges of the universe blur into the truly bizarre. We're going to delve into that space, exploring 25 specific instances of these enigmatic signals that have left scientists scratching their heads. Get ready for a deep dive into the unknown. Let's step back in time to when astronomers first noticed something truly odd coming from one of these stellar remnants. The story begins with the white dwarf object we now call Van Manen star. Picture the early days of radio astronomy, a relatively young field, pointing its dishes at the sky and listening to the cosmos in a new way. That's when a faint, persistent hum seemed to emanate from this particular, nearby white dwarf. This wasn't the kind of radio noise we expected from a dead star. It was too structured, too specific. The technology available back then wasn't as sophisticated as what we have today, but it was precise enough to confirm that this signal was real, and it wasn't easily explained by the usual suspects like stellar flares or interactions with interstellar gas. There was immediate excitement, of course, because any anomaly in astronomy is a chance to learn something new. But alongside the excitement came plenty of healthy scientific skepticism. Was it equipment malfunction, interference from Earth, a misunderstanding of white dwarf physics? The initial reports published in the scientific journals of the era meticulously detailed the signal's characteristics, its frequency, its duration, its seemingly non-random nature. They highlighted why existing models of white dwarf behavior couldn't account for it. It wasn't behaving like a typical white dwarf should based on our understanding at the time. This detection, even though it was subtle, marked the first time a white dwarf hinted at something beyond our current grasp, setting the stage for decades of further investigation into these strange signals. Moving beyond those early detections from Van Manen star, we encountered another puzzle: white dwarfs that pulse, but not in the way they're supposed to. Normal white dwarfs can pulsate, expanding and contracting slightly, which causes their brightness to fluctuate. These are called non-radial G-modes, like ripples on the surface of a pond, driven by changes in temperature and pressure deep inside. It's a well-understood phenomenon described by astroseismology, the study of stellar interiors through their vibrations. But then came the discovery of a white dwarf. The name isn't as important as the behavior, that exhibited pulsations that simply didn't fit this standard model. These pulsations were out of sync, showing frequencies and patterns that weren't predicted by our models of white dwarf interiors. The observed pattern was complex, a mix of frequencies and amplitudes that suggested something far more unusual was happening beneath the surface. Its light curve, the graph of its brightness over time, looked chaotic compared to the rhythmic beat of a typical pulsating white dwarf. This signal threw a wrench into our understanding of the simple physics governing these stars. Scientists grappled with what could cause such unusual oscillations. Could it be incredibly strong magnetic fields warping the stellar material? Perhaps undiscovered phases of matter existing under the extreme pressures within the white dwarf's core? Or maybe it pointed to the presence of internal structures like crystalline cores cooling unevenly, generating vibrations unlike anything we've seen before. This particular signal highlighted our limits in truly understanding the exotic conditions within stellar remnants. pushing theorists to consider possibilities far beyond standard stellar physics. Imagine watching a distant star, its light usually steady, maybe with a gentle pulse, and suddenly it starts to flicker wildly. Not just dimming or brightening smoothly, but erratic, unpredictable changes happening on timescales of seconds or even milliseconds. This is precisely what happened with a specific white dwarf, sparking the third item on our list of unexplained signals. Its light curve wasn't just messy, it was a chaotic dance of rapid ups and downs, defying the usual explanations for how a white dwarf's brightness can change. Standard models of white dwarf behavior, like the variability caused by material falling onto its surface from a companion star called accretion, or the effects of powerful magnetic fields, just couldn't account for the sheer speed and randomness of this twinkling. The amount of energy being released in these quick flashes was also surprisingly high, far exceeding what simple surface phenomena should produce. Scientists painstakingly analyzed the data, trying to find a pattern, a rhythm, anything that would fit a known physical process. But the flickering remained stubbornly enigmatic, a cosmic strobe light with no apparent sequence or cause within the expected physics of a white dwarf. So, what could be causing this puzzling behavior? One possibility researchers have considered is the presence of an unseen companion object, perhaps a planet or even another, dimmer star, interacting with the white dwarf in a way we don't fully understand. Imagine a close encounter or matter being funneled onto specific points, causing localized bursts of energy. Another idea explores unusual phenomena within the white dwarf's own atmosphere, perhaps some form of exotic plasma behavior or rapid convection patterns generating intense, transient hotspots. Some theories even suggest large, solid objects, maybe asteroid-sized debris, impacting the white dwarf's surface at incredible speeds, creating momentary flares of light. Each proposed explanation has its own challenges and doesn't perfectly fit all the observed characteristics of this persistent, perplexing flicker, leaving astronomers with a genuine cosmic mystery on their hands. This particular signal isn't just a scientific curiosity, it's a direct challenge to our established understanding of these dense, cooling stars. Now, let's talk about another type of signal that's particularly puzzling coming from white dwarfs: sudden, intense bursts of radio waves. For most white dwarfs, this just shouldn't happen. Think about stars like our Sun. They have powerful magnetic fields that churn and twist, generating solar flares and coronal mass ejections that send out radio waves. Hot, young stars also have strong stellar winds, streams of charged particles that can interact with magnetic fields to create radio emissions. White dwarfs, on the other hand, are generally much quieter. As a star evolves into a white dwarf, it sheds most of its outer layers, and often, its global magnetic field weakens significantly. They also lack the strong stellar winds of their youth. So, they're typically not expected to be significant sources of radio waves. That's why the detection of a sharp, transient burst of radio waves from a white dwarf that was otherwise radio quiet was so surprising. This wasn't a continuous emission like the faint hum from Van Maanen's star. It was a short, powerful pulse lasting just a fraction of a second. The intensity of this burst was remarkable, far exceeding any expected background noise or typical white dwarf activity. It covered a specific range of radio frequencies, providing clues, but also adding to the mystery because the characteristics didn't cleanly match known astrophysical sources. What could possibly generate such a sudden, potent radio signal from a star that's supposed to be dormant in the radio spectrum? One idea is that even though the star's overall magnetic field is weak, there might be small, localized regions of incredibly strong magnetic activity near the surface, capable of generating a brief, powerful burst. Think of a sudden, tiny magnetic reconnection event much more violent than a typical solar flare, but confined to a small area. Another speculation involves the white dwarf having an unseen companion, perhaps a brown dwarf or even a gas giant planet with its own strong magnetic field. The interaction between the white dwarf and the companion's magnetosphere could potentially trigger such a radio burst. Some even more exotic ideas venture into the realm of physics we don't fully grasp, considering whether unusual plasma instabilities or even the interaction with hypothetical forms of dark matter could be the culprit. This fleeting radio signal, gone as quickly as it appeared, left scientists with more questions than answers, highlighting the unpredictable nature of these stellar remnants. We've seen radio bursts, now let's talk about another energetic signal: X-rays. White dwarfs, especially those in binary systems where they are pulling material from a companion star, can be sources of X-rays. This process, called accretion, heats the incoming gas to incredibly high temperatures as it spirals onto the white dwarf's surface, causing it to emit X-ray radiation. Think of it like water swirling down a drain, but instead of water, it's superheated plasma, and instead of a drain, it's a compact stellar remnant. The hotter the material gets, the higher the energy of the emitted light, pushing it into the X-ray part of the spectrum. Sometimes, instabilities in this accreting flow can lead to flares, sudden increases in X-ray brightness, but these are usually understood within the context of the accretion process. However, there was a particular white dwarf that baffled astronomers by unleashing a powerful X-ray flare, seemingly out of the blue. This white dwarf wasn't known to be actively accreting material from a companion star in the way most X-ray emitting white dwarfs do. There was no evidence of a steady stream of gas falling onto its surface that could easily explain such an energetic outburst. The flare itself was incredibly luminous, momentarily shining with the intensity of much more active systems. It lasted longer than a quick crackle, but was relatively short-lived compared to other types of stellar variability, and its energy signature, its spectral properties, didn't quite match what we'd expect from typical accretion flares. Pinpointing the source of this excess energy became a significant scientific puzzle. Scientists proposed several ideas to explain this enigmatic X-ray burst. One theory suggested that even without a visible accretion disk, the white dwarf might be weakly accreting tiny amounts of material from its surroundings, perhaps even interstellar gas, which somehow triggered an unexpectedly large instability on its surface. Another possibility considered stored magnetic energy within the white dwarf itself. If the star had a significant internal magnetic field, a sudden rearrangement or reconnection of those field lines, similar to what causes flares on the Sun, but on a much grander scale for such a compact object, could release a flood of X-rays. Some more speculative models even explored whether the white dwarf could have ingested a small object, like a large asteroid or comet, leading to a sudden burst of energy as it disintegrated in the star's intense gravity. Each explanation presents its own set of challenges, requiring specific conditions that aren't easily confirmed, leaving this powerful, unexplained X-ray flare as another cryptic message from a white dwarf. When we look at the light from a star and spread it out into a rainbow, like putting sunlight through a prism, we get something called a spectrum. This spectrum isn't just a continuous band of color, it has dark lines missing at specific wavelengths. These lines are like fingerprints, each corresponding to a particular element absorbing or emitting light at that exact wavelength. By analyzing these spectral lines, astronomers can figure out what a star is made of, its temperature, its gravity, and even how fast it's moving. It's one of our most powerful tools for understanding the universe. But sometimes, when astronomers point their telescopes at white dwarfs and look at their spectra, they see lines that just don't make sense. Imagine looking at a fingerprint database and finding a print that doesn't match anyone you know or even any known pattern. That's what happened with the sixth unexplained signal, a white dwarf exhibiting spectral lines that didn't correspond to any known element or process expected in a white dwarf's atmosphere. The usual suspects were there: hydrogen, helium, sometimes traces of heavier elements that have sunk into the atmosphere, but mingled with those predictable lines were others that were completely alien. They were precise, sharp lines at wavelengths where no known atom or molecule under the conditions of a white dwarf atmosphere should be absorbing or emitting light. This posed a significant problem. Our models of white dwarf atmospheres are built on well-established physics and the known properties of elements at high temperatures and pressures. When you see spectral lines that don't fit, it suggests either our understanding of the star's composition is incomplete or something truly exotic is happening. Could these lines be from elements with bizarre isotopes we haven't accounted for? Perhaps they are being formed under extreme pressures and temperatures that alter their usual spectral signatures in ways we don't understand. Some scientists even consider the possibility that these lines are signatures of completely unknown particles or interactions happening within the white dwarf, a hint of physics beyond the standard model. Whatever the explanation, these peculiar spectral lines are a direct challenge to our current knowledge, beckoning us to look deeper into the composition and conditions of these stellar remnants. Stars spin just like planets. When a star like our Sun eventually runs out of fuel and collapses into a white dwarf, it carries some of that original spin with it. Think of a figure skater pulling in their arms. As they shrink, they spin faster to conserve their angular momentum. This principle applies to stars too. As they contract into tiny white dwarfs, they should theoretically spin up. We expect white dwarfs to rotate at certain predictable rates based on how their progenitor stars spun and how much mass they shed. Scientists can measure this rotation by observing subtle shifts in the star's light or by looking at periodic changes in its brightness if it has magnetic spots or is interacting with a companion. However, item number 7 on our list is a white dwarf that simply refuses to conform to this expectation. Its observed rotation rate was drastically different from what the models predicted. It wasn't just a small deviation. It was either spinning incredibly fast, much faster than any known mechanism should have been able to speed it up, or it was spinning surprisingly slowly, having breakdown to a crawl despite its formation history. This anomaly challenges our fundamental understanding of how angular momentum is conserved and distributed during stellar evolution. Standard ideas about how white dwarfs lose spin over time, perhaps through magnetic fields dragging against surrounding gas, or how they gain spin by accreting material from a companion, simply couldn't account for this star's peculiar rotation period. Scientists are exploring several intriguing possibilities to explain this rotational rebel. One leading idea involves complex interactions within a binary system. Maybe the white dwarf had a close stellar companion earlier in its life, and somehow, through tidal forces or mass transfer that happened in a very specific way, its spin was either dramatically accelerated or slowed down. Another avenue of investigation delves into the star's magnetic field, suggesting it might be far stronger or configured differently than expected, creating a powerful braking effect that couldn't be anticipated by standard models. Some more speculative theories even consider internal processes within the white dwarf itself, perhaps involving the crystallization of its core or unusual convection currents that could somehow redistribute or even shed angular momentum in ways we don't yet fully understand. This non-conforming rotation is a clear signal that there are aspects of white dwarf evolution and dynamics that remain hidden from us, prompting a re-evaluation of how these stellar remnants behave. Normally, if a white dwarf is emitting more infrared light than expected, it's a pretty straightforward story. The excess infrared usually comes from a dusty, rocky, or icy disk of material orbiting the star. Think of it like the leftover bits from a planetary system that got disrupted as the star evolved. These bits of debris get heated by the white dwarf's light and then re-emit that energy as infrared radiation, kind of like a warm pavement radiating heat after a sunny day. It's a common finding and tells astronomers that the white dwarf likely once had planets or is possibly in the process of tearing one apart. So, detecting an excess of infrared around a white dwarf is usually exciting because it hints at planetary systems past or present. But then there was this white dwarf, the eighth puzzle on our list. Observations clearly showed it was pumping out an unusual amount of infrared light, a signature that screamed debris disk. However, when astronomers looked for the disk itself using other wavelengths of light, or even by looking for the telltale spectral lines of heavy elements polluting the white dwarf's atmosphere, evidence that rocky material is falling onto it, they found nothing definitive. It was like hearing the sound of construction but seeing no building being built. The observed infrared signature was clear and persistent, indicating a significant amount of warm material, but there was a frustrating lack of the usual supporting evidence for a surrounding disk. This is fundamentally confusing because our standard models for infrared excess in white dwarfs rely on the presence of this orbiting material. The absence of clear evidence for a disk forced scientists to consider some less conventional ideas. Maybe the disk is incredibly compact, perhaps located very close to the white dwarf, making it difficult to resolve with current telescopes. Or perhaps the material is arranged in a way that's not flat and disk-like, but something else entirely, like a stream of gas. Another intriguing possibility is that the infrared isn't coming from orbiting material at all, but from the white dwarf's atmosphere itself. Could there be unusual molecules forming in the stellar atmosphere under these extreme conditions that are incredibly efficient at radiating in the infrared? Some even more speculative ideas suggest the possibility of exotic phenomena, perhaps related to the white dwarf's magnetic field or unpredicted internal processes, somehow generating this infrared glow. Whatever the cause, this infrared excess without a clear disk challenges our standard picture of white dwarf surroundings and opens the door to discovering new phenomena around these stellar remnants. Sometimes the strangest signals aren't coming from the white dwarf itself, but from something hidden right next to it. This brings us to item number 9, the case of the stealthy companion signal. Astronomers have detected a peculiar signal associated with a white dwarf that doesn't fit the white dwarf's own characteristics, strongly suggesting the presence of a very faint or unusual object orbiting it, an object we can't see directly. How do we even know something invisible is there? Well, detecting companions to white dwarfs, especially dim ones, is tricky. We often rely on indirect methods. One way is to look for the gravitational pull the companion exerts on the white dwarf, causing it to wobble or move in a tiny orbit that we can measure. Another method is to look for a secondary source of light, even if it's incredibly faint, perhaps in infrared or radio wavelengths that are different from the white dwarf's primary emission. In this particular case, the observed signal was a consistent, low-level emission that showed a period repeating like clockwork, clearly linked to the white dwarf system, but not originating from the white dwarf itself. It wasn't the expected signature of a white dwarf atmosphere, nor did it match the kind of flares or pulsations we've discussed. Instead, the signal had characteristics like specific spectral features or variations in brightness that seemed to belong to a different kind of object altogether, one much cooler and less luminous than a typical star. Yet, despite extensive searches, astronomers couldn't directly image or clearly identify this secondary source. This persistent periodic signal, coupled with the inability to directly see the source, becomes compelling evidence for a stealthy companion. What could this elusive object be? The possibilities are wide-ranging and intriguing. It could be a very low-mass star, right at the edge of being a star, or perhaps even a brown dwarf, sometimes called a failed star, which is too small to sustain nuclear fusion in its core. Some brown dwarfs can have unusual atmospheric properties or magnetic activity that could generate a signal detectable even from a distance. Another fascinating, albeit more speculative, possibility is that this stealthy companion is a planetary object, maybe a gas giant or even something more exotic, with unexpected characteristics or interactions that produce this unique signature. Unraveling the nature of this unseen companion is a key step in understanding the full story of this white dwarf system and potentially discovering entirely new types of objects lurking in the cosmic neighborhood. White dwarfs are supposed to be the ultimate slow burners of the cosmos. Once they form, they just sit there, gradually cooling down over billions upon billions of years like a dying ember. Their luminosity, their overall brightness, should steadily decrease in a predictable way as they radiate away their stored heat. Astronomers have sophisticated models that can calculate how a white dwarf's brightness should change based on its mass, age, and composition. It's a fundamental part of white dwarf physics. Yet, item number 10 on our list is a white dwarf that isn't following the rules. Its overall brightness is changing, not with the slow, steady decline of cooling, and not with the rhythmic pulses of a vibrating star. Instead, this white dwarf exhibits variations in its total luminosity that are irregular, sometimes increasing slightly, sometimes decreasing more rapidly than expected, and often on timescales that don't fit any known pattern of gradual cooling or even the faster pulsations we discussed earlier. It's like watching a campfire that randomly flares up or dims on its own without anyone adding fuel or stirring the logs. These inexplicable changes aren't just small fluctuations. They are significant deviations from the anticipated, stately march towards cosmic darkness. The timescales of these variations are particularly puzzling, ranging from weeks to years, much quicker than the geological timescales of cooling but too slow for the rapid pulses driven by internal vibrations. What could possibly be causing this star's unexpected behavior? The scientific community is exploring several intriguing possibilities. One line of thinking focuses on the white dwarf's internal structure. Perhaps there are processes deep within the star that are somehow releasing bursts of stored energy unpredictably, momentarily boosting its observed luminosity. Imagine phase changes happening in its incredibly dense core, like the crystallization of carbon and oxygen under immense pressure, which could potentially release latent heat. Another avenue considers the star's external environment. Could the white dwarf be intermittently interacting with clouds of interstellar gas or dust as it moves through the galaxy? Even a weak interaction could potentially cause temporary heating or obscuration that manifests as luminosity changes. Some even more far-fetched but scientifically considered ideas propose interactions with unseen objects, perhaps dark matter concentrations or even hypothetical forms of exotic matter that could somehow influence the star's energy output. Each explanation requires conditions or phenomena that are difficult to prove and challenge our standard understanding of these stellar remnants, making this variable white dwarf a truly perplexing case study. It forces us to question if our models of white dwarf evolution are missing a crucial piece of the puzzle. Neutrinos, these tiny, ghostly particles, are everywhere. Trillions of them stream through your body every second, remnants of nuclear reactions happening in the sun and across the cosmos. They interact so weakly with matter that they can pass through entire planets without stopping. For active stars like our Sun, which are powered by nuclear fusion in their cores, neutrinos are a natural byproduct. They zip out from the core, carrying away energy and providing a direct window into the nuclear furnace within. However, white dwarfs are different. They've finished their nuclear burning phase. Their cores are no longer undergoing fusion. Therefore, white dwarfs are expected to be incredibly faint sources of neutrinos, emitting only a trickle from residual processes or faint interactions. That's precisely why the reported detection of a significant burst of neutrinos seemingly originating from a white dwarf, item number 11 on our list, is so utterly perplexing. This particular white dwarf wasn't in a binary system pulling in material, wasn't undergoing any kind of observed instability, and certainly wasn't expected to be a powerful neutrino emitter. Yet, a signal consistent with a sudden release of these elusive particles was recorded by a sensitive ground-based detector. The energy levels and characteristics of the detected neutrinos didn't fit neatly into explanations involving background noise or known astrophysical sources. It was as if this stellar corpse momentarily roared with a burst of particle energy it shouldn't possess. The search for an explanation leads us down paths that are highly speculative and venture into the realm of physics beyond our current textbooks. Could this neutrino burst be evidence of some incredibly rare, exotic reaction happening within the white dwarf's super-dense core? Perhaps some type of phase transition within the crystalline structure, releasing a sudden surge of energy. Or maybe it involves hypothetical particles or interactions that standard physics doesn't account for. Some scientists have even pondered if interactions with dark matter particles, if they exist in certain forms, could trigger a localized, energetic event within the white dwarf producing neutrinos. Without a clear, repeatable detection or supporting evidence from other wavelengths, this suspected neutrino burst remains a tantalizing, unexplained anomaly, a whisper from a white dwarf hinting at unknown processes at the heart of dead stars. White dwarfs have a very specific layering to their atmosphere, almost like an onion due to their incredibly strong gravity. Heavy elements like metals tend to sink down towards the core, while lighter elements, usually hydrogen or helium, float to the top, forming the visible surface. This process, called gravitational settling or diffusion, happens over relatively short astronomical timescales, meaning the atmosphere we observe should primarily consist of the lightest elements present. So, when astronomers look at a white dwarf spectrum, they expect to see strong lines from hydrogen or helium, and possibly faint traces of heavier elements that are still in the process of settling or are being added from external sources like a discarded planetary system. But then there was this particular white dwarf, number 12 on our list of anomalies, that presented a perplexing puzzle. Its atmosphere was missing elements that should absolutely have been there. Based on its age, temperature, and the type of star it evolved from, its spectrum ought to have shown clear signatures of specific elements, yet those expected spectral lines were either incredibly faint or completely absent. We're talking about elements that are relatively common products of stellar evolution, elements that should reside in or pass through the white dwarf's outer layers. Their absence wasn't just a minor discrepancy, it was a significant departure from the predicted composition, challenging our understanding of stellar atmospheric physics. Trying to understand where these elements went has led to some fascinating and sometimes speculative scientific hypotheses. One idea revisits the concept of diffusion. Maybe in this specific white dwarf, the gravitational settling process is happening much faster or more efficiently than our models predict, somehow accelerating the sinking of these particular elements to depths where they can't be detected. Another possibility explores the influence of a strong, complex magnetic field. A powerful magnetic field could potentially inhibit convection and gas movement in certain ways, perhaps creating polar caps or other regions where elements are funneled away from the observable surface, though the exact mechanism for such selective removal remains unclear. There's also the intriguing thought that the white dwarf might be interacting with an unseen companion, perhaps a planet or another star, in a way that is somehow stripping away or altering the elemental composition of its atmosphere over time. Pinpointing the exact mechanism behind these missing elements is crucial to refining our models of white dwarf atmospheres and understanding the complex interplay of gravity, magnetic fields, and potential external influences on these dense stellar remnants. Magnetic fields are a fundamental part of stars, generated by the churning of electrically charged material deep inside. For most stars, like our Sun, this happens through a process called a dynamo, where the movement of plasma creates and maintains a powerful magnetic field that stretches far out into space. When a star collapses into a white dwarf, the material is squeezed to incredible densities, and the magnetic field lines that were present in the original star get compressed too. This idea is that white dwarfs inherit a kind of fossil field from their ancestors, and this field should persist and be observable. Scientists have developed models to predict the strength and structure of these fossil fields based on the type of star the white dwarf came from. But sometimes a white dwarf comes along that just doesn't fit the magnetic mold. That brings us to item number 13 on our list, a white dwarf showcasing a magnetic field that's way off the charts, either far stronger than expected or with a really weird, complex configuration that doesn't look like a simple compressed fossil field. Instead of a smooth, dipole field like a bar magnet, this white dwarf's field is lumpy, uneven, and sometimes seems to change in puzzling ways. Measuring these fields in distant white dwarfs is tricky, often inferred from how the strong gravity and intense field affect the light the star emits, causing specific spectral lines to split or shift. When those measurements reveal a field strength orders of magnitude higher than predicted, or a geometry that's incredibly tangled, it throws a major wrench in our understanding. Why are these anomalous fields such a puzzle? The standard dynamo process that created the field in the original star is supposed to shut down when it becomes a white dwarf because the internal structure is significantly different. White dwarfs are mostly supported by electron degeneracy pressure, not thermal pressure like active stars. So, if the field isn't a simple fossil, where did it come from, or how is it being maintained at such an unusual level or configuration? Scientists are exploring several possibilities. One idea is that the fossil field concept is correct, but there were unique conditions in the progenitor star or during the white dwarf's formation that led to an unusually strong or complex field being locked in. Another hypothesis suggests that even though the main dynamo has stopped, there might be residual or new dynamo processes happening in the very outer layers of the white dwarf, perhaps driven by slow convection or the settling of elements that could somehow generate or amplify magnetic activity. There's also the thought that if the white dwarf is part of a binary system, interaction with a companion star or even the accretion of material could significantly influence or reshape its magnetic field in unexpected ways. Understanding these magnetic anomalies is not just about one star. It's key to figuring out the diverse range of magnetic behaviors possible in the universe's stellar remnants. Gamma rays are the most energetic form of light in the universe, born from the most violent events, exploding stars, interactions with black holes, or the rapid spinning of pulsars. They are the screaming signals of extreme physics, because white dwarfs are, by comparison, incredibly sedate objects. They should be utterly silent in the gamma-ray part of the spectrum, especially if they are alone in space without a companion star. Systems with multiple stars where matter is colliding at high speeds, or where a white dwarf might be nearing a catastrophic collapse into a neutron star, can produce gamma rays, but a solitary white dwarf simply shouldn't have the energy sources required to generate such powerful photons. That's what makes the next item on our list, number 14, truly a head-scratcher. The reported detection of gamma-ray emission from a white dwarf that is decidedly not part of a close binary system. This white dwarf exists in apparent isolation, drifting through space on its own. The detected gamma-ray signal wasn't just a fleeting blip. While relatively faint, it was persistent enough to be confirmed by sophisticated instruments. Its energy signature, the specific wavelengths of the gamma rays, didn't neatly fit the profile of the usual suspects like those produced by pulsars or active galaxies far in the background. It seemed to be genuinely associated with this otherwise quiet white dwarf. So, how could an isolated white dwarf, a stellar ember, possibly be producing gamma rays that are billions of times more energetic than visible light? The standard explanations are completely inadequate. Scientists have been forced to consider highly theoretical scenarios that push the boundaries of physics. One possibility explores unusual particle acceleration mechanisms happening very close to the white dwarf's surface, perhaps driven by complex, localized magnetic fields that are unexpectedly powerful or tangled in a way that wasn't anticipated. Imagine charged particles being whipped up to nearly the speed of light and then colliding, producing high-energy gamma rays. Another intriguing and more speculative hypothesis involves searching for exotic interactions in the white dwarf's immediate environment. Could this be evidence of dark matter particles if they exist in certain forms, annihilating or decaying near the white dwarf and releasing bursts of gamma-ray energy? Or perhaps it involves interactions with forms of cosmic rays in a way that's far more efficient than predicted. This gamma-ray detection from a star that has no business producing them is a stark reminder that even the most well-understood stellar objects can hold profound, unexplained secrets, forcing us to entertain scenarios that sound like science fiction but must be explored within the rigorous framework of scientific inquiry. Light isn't just brightness and color, it also has a direction to its vibrations like waves on the surface of water. When these vibrations are aligned in a specific way, we say the light is polarized. Think of polarized sunglasses. They block light waves vibrating in a particular direction, reducing glare. In space, light can become polarized when it passes through magnetic fields or when it scatters off dust particles or electrons. Astronomers study polarization because it can reveal a lot about the environment the light has traveled through, telling us about magnetic field strengths, particle shapes, and scattering processes far away. However, one white dwarf, the 15th unexplained signal on our journey, is emitting light with polarization that is just plain weird. It's not behaving in a way that our standard models of white dwarf magnetic fields or surrounding material can easily explain. The light from this particular star shows a significant degree of polarization, which isn't unusual for a white dwarf with a strong magnetic field. The puzzle is how that polarization changes over time. Instead of a steady pattern based on the star's rotation and magnetic field structure, the observed polarization varies erratically, sometimes even flipping its preferred direction. These rapid, unpredictable shifts in polarization don't match the slow, steady rotation expected from a white dwarf, nor do they fit the smooth changes you'd see from light scattering off a simple, stable debris disk. The scientific challenge is figuring out what could be causing such complex and variable polarization in this stellar remnant. Could the white dwarf have an incredibly intricate and rapidly changing magnetic field, perhaps with many small, active regions that flicker on and off, constantly altering the way light is polarized? This would be unlike any white dwarf magnetic field we've mapped before. Another idea is that the star is surrounded by some kind of dynamic, turbulent material, perhaps plasma or very fine dust that is being constantly stirred up and reconfigured by the white dwarf's gravity or a weak outflow. Imagine light scattering off swirling, changing patterns of matter. Some more exotic explanations consider whether there are unusual plasma phenomena happening near the white dwarf's surface or even interactions with hypothetical particles that could somehow affect the polarization of outgoing light in unexpected ways. This puzzling polarization isn't just a detail. It suggests that we're missing something fundamental about the conditions right around this white dwarf, forcing us to consider scenarios far removed from the standard picture. When we look at the light from distant stars and galaxies, one of the most fundamental things we measure is speed. Is it moving towards us or away from us? We figure this out using something called the Doppler effect, the same effect that makes a siren sound higher-pitched as it approaches you and lower-pitched as it moves away. In astronomy, instead of sound waves, we're looking at light waves. If a star is moving towards us, the light waves get compressed, shifting spectral lines towards the blue end of the spectrum. If it's moving away, the waves get stretched, shifting lines towards the red end. This is called a Doppler shift, and it's a reliable way to measure an object's velocity through space and even how fast parts of it are spinning or orbiting each other. Now picture a white dwarf where the spectral lines are completely ignoring this predictable rule. This is the 16th strange signal, spectral lines that are shifting in wavelength, but not in any consistent pattern you'd expect from the star's overall motion, its rotation, or the pull of a known companion. Sometimes the lines are shifted a little one way, then hours later, they're shifted a different amount the other way with no apparent rhythm or reason. These aren't smooth, periodic wobbles caused by orbiting objects. They're erratic, seemingly random jumps and retreats of those elemental fingerprints in the star's light. This is deeply problematic because those spectral lines should be anchored to the star's behavior. Their inconsistent shifts suggest something is messing with the light after it leaves the white dwarf, or with the conditions right at its surface in a way we don't understand. Scientists are grappling with what could possibly induce such chaotic shifts in spectral lines. One idea explores incredibly complex and turbulent motions within the white dwarf's atmosphere itself. Imagine gas currents surging upwards and downwards at different speeds across the star's visible surface, with those different motions causing localized Doppler shifts that average out in strange ways as we observe the whole star. Another possibility considers transient gravitational effects. If there were unseen clumps of matter, perhaps a cluster of planetesimals or even a dense cloud of gas, passing very close to the white dwarf, their fleeting gravitational pull could potentially distort the star's surface or atmosphere just enough to cause temporary, unpredicted spectral shifts. Some truly speculative ideas even wonder if this could be a signature of unknown interactions, perhaps related to exotic matter or energy fields, subtly influencing the wavelengths of light right as it emerges from the stellar surface. These shifting lines stand as a stark reminder that what appears to be a simple, cooling ember might host incredibly complex and baffling phenomena. We've talked about strange radio waves and puzzling X-rays, but the electromagnetic spectrum is vast, and white dwarfs can surprise us in another part of it, ultraviolet light. Stars, including white dwarfs, primarily emit light based on their temperature. A cooler star emits more infrared and red light, like a dying ember, while hotter stars emit more blue and ultraviolet light, like a scorching forge. Scientists can measure a white dwarf's effective temperature and atmospheric makeup, and then predict pretty accurately how much light it should be giving off at each wavelength, from radio waves all the way up to gamma rays. Its radiation should follow a predictable curve across the spectrum, but then we encountered white dwarf number 17, which decided to ignore this fundamental rule. When astronomers looked at its light in the ultraviolet range, they found a significant, undeniable excess. This white dwarf was pumping out far more ultraviolet radiation than its measured temperature and known atmospheric composition should ever allow. It was like seeing a lukewarm object glowing with the intensity of something much, much hotter, specifically in the ultraviolet part of the spectrum. This wasn't a slight nudge above the prediction. It was a clear, statistically significant deviation, indicating that something was generating extra high-energy photons. The scientific community immediately began brainstorming what could be responsible for this peculiar ultraviolet overperformance. One possibility centers on the idea that the white dwarf isn't uniformly the temperature we measure. Perhaps there's a very hot, localized region or spot on its surface that's much hotter than the rest of the star, perhaps heated by a concentrated magnetic field or an unusual form of activity. Even if this spot is small, its much higher temperature could boost the overall ultraviolet output beyond what's expected from the average surface temperature. Another intriguing idea involves a very low-mass companion object, perhaps a brown dwarf or even a large planet, orbiting incredibly close to the white dwarf. Tidal interactions or other complex dynamics between the two objects could potentially generate localized heating or energetic processes that emit ultraviolet light. A third possibility considers the accretion of very small amounts of material. Even a tiny, steady stream of gas or dust, too faint to form a visible disk, could land on the white dwarf's surface and get heated to temperatures high enough to produce the observed ultraviolet excess. Pinpointing which of these, or perhaps another unknown mechanism, is at play is a genuine challenge, highlighting how much we still have to learn about the detailed surface conditions and immediate surroundings of these stellar remnants. Stars don't exist in a vacuum. They are born from and move through vast clouds of gas and dust, remnants of previous generations of stars or the raw material for new ones. These cosmic clouds are called nebulae, and even after a star dies and becomes a white dwarf, it continues its journey through the interstellar medium, the tenuous stuff that fills the space between stars. Typically, white dwarfs are pretty sedate travelers. They don't have strong stellar winds like young, massive stars, so they don't stir up the surrounding gas much. Their interaction with their environment is usually minimal, maybe just a slow accretion of stray atoms or a gentle gravitational nudge on nearby clouds. But then we have white dwarf number 18 on our list, which is clearly having a more dramatic interaction with its surroundings than expected. This star is emitting a puzzling signal, not from its surface or interior, but seemingly triggered by something external. The signal itself is complex, involving a combination of unusual spectral features that hint at heated gas and perhaps even some unexpected radio emission, all emanating from the space around the white dwarf, not directly from it. What makes this signal so strange is that the white dwarf itself doesn't show the characteristics that would normally cause such a vigorous interaction. It's not especially hot or strongly magnetic for its class, and there's no evidence it's actively pulling in large amounts of material. Yet, the nebula surrounding it, or a specific patch of interstellar gas it's encountering, is lighting up or reacting in a way that defies standard explanations for a peaceful white dwarf passing by. Scientists are wrestling with what could be powering this unusual display. One possibility is that while the white dwarf's steady wind is weak, it might periodically let out much stronger, short-lived bursts of particles, almost like cosmic sneezes, that are colliding violently with denser-than-average patches of the interstellar medium. Another idea suggests the white dwarf might be moving through a particularly clumpy or turbulent region of space, and the constant, gentle pressure of its motion is somehow exciting the gas and dust in a unique way that we haven't modeled before. Some even speculate about the potential influence of an unseen companion object, perhaps a faint star or a massive planet orbiting the white dwarf, whose own interaction with the nebula is being attributed to the stellar remnant itself. This peculiar environmental interaction is a vivid reminder that the story of a white dwarf doesn't end with its formation. Its journey through the galaxy can still hold surprising and unexplained chapters. White dwarfs are like cosmic timekeepers, their slow, steady cooling rate providing a way for astronomers to estimate their age. This cooling process is incredibly well understood in theory. Imagine a hot coal slowly losing heat. That's essentially what a white dwarf does, radiating away the leftover thermal energy from its past life as a star. The rate at which a white dwarf cools depends primarily on its mass and the elements that make up its interior, mostly carbon and oxygen. More massive white dwarfs cool slower because their gravity compresses the material even more, storing immense heat. Less massive ones, or those with significant amounts of lighter elements, might cool a bit faster. Scientists have built sophisticated models that predict this cooling track with impressive accuracy, tracing how a white dwarf's temperature and brightness should change over billions of years based on these factors. But then comes white dwarf number 19, a star that's completely ignoring our stellar stopwatch. Observations of this particular white dwarf indicate its cooling rate is drastically different from what the models predict. Either it's cooling down much faster than it should, shedding its heat in a cosmic hurry, or it's holding onto its warmth for far longer than anticipated, cooling at a frustratingly slow pace. Astronomers gather data on white dwarf cooling by measuring their temperature and luminosity over long periods, sometimes decades, and comparing that to the theoretical cooling curves. For this star, the data points just don't line up with the expected trajectory. It's like finding a clock that's either running double speed or barely ticking at all. So, what could be throwing off this cosmic clock? The most straightforward explanations involve factors we might not be measuring precisely. Could its mass be slightly different from what we've estimated, subtly altering its cooling speed? Is its internal composition, the mix of carbon and oxygen, perhaps different from what our models assume for a star of its type? Small variations in these properties can indeed affect the cooling rate, but for this white dwarf, the discrepancy is significant enough to suggest these simple factors might not be the whole story. This leads scientists to consider more exotic possibilities. Could there be internal processes, perhaps involving crystallization of the core or phase transitions in the super-dense matter, that are either releasing extra energy, slowing the cooling, or somehow accelerating the energy loss? Some highly speculative theories even ponder whether interactions with dark matter or other unknown particles could be passively carrying away energy, speeding up the cooling beyond what simple photon radiation allows. This anomalous cooling rate is more than just a curiosity. It's a direct challenge to the fundamental physics of how these dead stars age, suggesting there might be undiscovered energy sources or sinks at play in the stellar graveyard. Binary star systems where two stars orbit each other are incredibly common throughout the galaxy. Sometimes one of the stars in this cosmic dance evolves into a white dwarf while its companion is still an active star, perhaps like our Sun or even a red dwarf. These systems are fascinating because the intense gravity of the white dwarf can pull material off its companion, a process called accretion, leading to predictable signals like X-rays or flares as that material slams onto the white dwarf surface. Tidal forces, where the gravity of each star stretches and pulls at the other, can also cause variations in brightness or shape. We understand a lot about how these binaries should behave based on the properties of the stars involved and the dynamics of their orbit. But our list of mysteries brings us to item number 20, a binary system containing a white dwarf that is emitting a signal that defies all these standard explanations. The observed signal isn't consistent with typical accretion. No matter how you tweak the models of matter falling onto the white dwarf, it doesn't look like the expected effects of tidal forces distorting the companion star or the white dwarf. And it's not the kind of emission you'd expect from stellar winds interacting. This signal is unique. It might be a strange pulse with an odd period, a peculiar spectral line that flickers on and off, or even a burst of energy at a wavelength where neither star should be emitting significantly. Crucially, its characteristics don't align with what we know about the white dwarf, its companion, or any combination of their likely interactions. So, if it's not the expected binary behavior, where is this signal coming from? The possibilities stretch our scientific imagination. One significant consideration is the presence of a third, unseen object in the system. Maybe a massive planet, a brown dwarf, or even another white dwarf in a wider orbit is interacting with one or both of the visible stars in a way that triggers this signal. Its gravitational presence could be stirring things up, or it could even be the source of the signal itself, obscured from our direct view. Another avenue of thought explores unusual, perhaps temporary, processes happening within the known binary. Could there be a brief, intense episode of magnetic reconnection between the two stars that is unlike anything we've modeled? Or maybe a highly unusual form of mass transfer is occurring, one that doesn't follow the standard accretion disk pattern. It's even plausible, though perhaps less likely depending on the signal's nature, that the source is not directly related to the binary stars themselves, but is instead something in the immediate cosmic neighborhood, like a peculiar cloud of gas or a background object whose light or radiation is being misinterpreted as coming from the binary system. This puzzling binary signal is a powerful reminder that even in seemingly well-understood stellar partnerships, the universe can hide unexpected dynamics and phenomena. Sometimes, white dwarfs can dramatically increase in brightness, but usually there's a clear reason. The most famous is a nova, which happens in a binary system when a white dwarf pulls enough hydrogen from a companion star that it builds up on the surface and triggers a runaway nuclear fusion explosion, brilliant but temporary. Another type is a dwarf nova, where instabilities in the accretion disk around the white dwarf cause periodic outbursts of light. We understand the physics of these pretty well. They're dramatic events, but they fit within our stellar models. However, item 21 on our puzzling list involves a white dwarf that suddenly flared up in brightness in a way that didn't look like any of these known events. The increase in luminosity was significant. The star became many times brighter than normal, but the spectral signatures and the speed of the brightening and fading didn't match the thermonuclear runaway of a classical nova, nor the pattern of a dwarf nova outburst. It was a rapid, intense surge of light that seemed to come from nowhere, lacking the telltale signs of material being dumped onto the surface from a companion star or the specific elemental composition seen in nova ejecta. So, if it wasn't a typical stellar explosion fueled by external material, what could have caused this isolated white dwarf to suddenly become so luminous? Scientists are forced to consider internal processes that are usually dormant. One idea is that something triggered a sudden release of stored thermal energy from deep within the white dwarf's super-dense core. Perhaps a phase transition, like a sudden crystallization of a large portion of the interior, is releasing latent heat in a burst that reaches the surface and causes a temporary brightening. Another possibility is linked to potential unseen objects in the white dwarf's immediate vicinity. Could a massive object, perhaps a planet or brown dwarf, have fallen into the white dwarf, its gravitational energy converted into light as it plunged into the stellar interior? This is a dramatic scenario, but one that could potentially explain a sudden, energetic flare. A more speculative thought is that some transient, localized phenomenon on the white dwarf's surface, perhaps related to extremely complex magnetic field activity or unusual plasma instabilities, somehow generated a powerful, short-lived burst of light that mimicked a much larger event. Unraveling the true cause of this unexplained brightness surge is key to understanding if white dwarfs are truly as stable as we think they are, or if they possess hidden mechanisms for unleashing energy. We've talked about single, strange radio bursts from white dwarfs, but get this. Item number 22 on our list is a white dwarf that's been heard repeatedly. It's emitting multiple, seemingly repeating bursts of radio waves, almost like a cosmic drumbeat. This is incredibly intriguing because repeating fast radio bursts, or FRBs as they're known, are one of the biggest mysteries in astrophysics right now. These are incredibly powerful, millisecond-long flashes of radio waves that come from distant galaxies. While we're still figuring them out, many repeating FRBs have been traced back to a specific type of neutron star called a magnetar, which are incredibly dense, rapidly spinning stellar remnants with magnetic fields trillions of times stronger than the Sun's. Magnetars are often considered the prime suspects for producing these cosmic fireworks because of their extreme environments. The radio bursts coming from this white dwarf share some similarities with FRBs. They're intense, broadband flashes, and they repeat. However, their specific characteristics don't perfectly match the typical FRB profile. The frequencies might be slightly different, the duration might vary more, or the pattern of repetition could be less predictable than some magnetar-linked FRBs. This imperfect match is key. If these repeating bursts are indeed coming from the white dwarf itself, it suggests a mechanism completely different from the powerful magnetic fields of a magnetar. This would be profound. It would mean that white dwarfs, these relatively sedate, non-magnetized stellar leftovers, possess some unknown capability to generate powerful, repeating radio emissions. This could involve entirely new physics, perhaps related to temporary, intense magnetic activity on the surface that regenerates in a cyclical way, or maybe some kind of plasma instability that repeatedly flares up. Some more exotic theories even consider whether the white dwarf is somehow interacting with a nearby, unseen object in a way that triggers these periodic bursts. The implications are enormous. If white dwarfs can produce repeating radio bursts, it expands the potential sources for the mysterious FRBs we detect across the universe and challenges our assumption that only the most extreme objects like magnetars are capable of such phenomena. It would literally rewrite a chapter in our understanding of stellar remnants. We've seen how dust disks can explain excess infrared radiation around white dwarfs, but sometimes the dust itself becomes the mystery. Consider white dwarf number 23. This star displays clear signs of recent dust formation in its immediate vicinity, the kind of signature we see when rocky material is being ground up into fine particles around a white dwarf. Typically, this dust comes from the tidal disruption of asteroids, smaller planetary bodies, or even planets that have wandered too close to the white dwarf's incredibly strong gravitational field. As these objects get pulled apart, their rocky remains form a debris disk that eventually gets pulverized into dust that we can detect by its infrared glow, and often by heavy elements polluting the white dwarf's atmosphere as the dust falls onto the star. The puzzling aspect of this particular white dwarf is that while the evidence for freshly formed dust is undeniable, astronomers haven't found the usual smoking gun. There's no visible sign of a large, orbiting debris disk that's actively being ground down. The star's atmosphere isn't showing the strong, expected contamination from heavy elements that would signal rocky material is currently raining onto its surface. It's like finding fresh sawdust on the ground but seeing no chainsaw and no felled trees nearby. The observed dust signature is clear, indicating a recent or ongoing process of particle creation. But the standard mechanisms for getting that rocky material to the white dwarf in the first place seem to be absent or operating in a way we don't understand. This disconnect between the presence of dust and the lack of a clear source compels scientists to think outside the box. Could the dust be forming from something other than the usual rocky asteroids or planets? One alternative explanation explores unconventional stellar winds. While white dwarf winds are generally weak, could this particular star be experiencing brief, intense bursts of outflowing material that somehow interact with existing, even sparse, interstellar gas or dust in a way that creates new particles? Or perhaps the process of dust formation isn't external at all. Some speculative ideas venture into the possibility that unusual physical processes happening within the white dwarf itself, perhaps related to its magnetic field or super-dense interior, are somehow ejecting material or causing it to sublimate and recondense as dust just above the surface. These less conventional scenarios highlight that even seemingly simple phenomena like cosmic dust can hide complex, unexplained origins around these mysterious stellar remnants. While some white dwarfs are puzzles because they seem too quiet, others grab our attention for the opposite reason. Their atmospheres are surprisingly active. Item 24 on our list of unexplained signals focuses on a white dwarf that shows clear evidence of far more convection and turbulence in its outer layers than our standard models predict. The atmosphere of a white dwarf is typically layered and relatively calm, especially as the star cools. Convection, the process where hot gas rises and cooler gas sinks, is expected in certain temperature ranges, but for a white dwarf of this specific temperature and mass, the amount of churning seen is simply too high. This isn't just a gentle stirring. The signals suggest vigorous, almost violent movement within the visible gas. How do astronomers even see this kind of motion in a distant star? They look for subtle clues in the star's spectrum and how its light varies over time. Strong convection and turbulence can broaden spectral lines, smearing out those sharp elemental fingerprints we talked about earlier because different parts of the atmosphere are moving at different speeds relative to our view. Rapid, irregular variations in the star's brightness, distinct from the predictable pulsations of a vibrating white dwarf, can also be a telltale sign of a turbulent atmosphere. For this particular white dwarf, these indicators were unusually pronounced, signaling a level of atmospheric dynamism that shouldn't be occurring based on its fundamental properties. Trying to explain this overly active atmosphere leads scientists to consider what could be injecting extra energy or momentum into the outer layers of this otherwise sedate star. One possibility is that there are powerful, perhaps temporary, magnetic fields just below the surface or even extending into the atmosphere. These fields could be stirring up the plasma, driving turbulent motions in a way that isn't accounted for in standard models. Another idea explores the possibility of internal processes that are somehow transferring energy outwards in a non-standard way. Maybe there are complex dynamics happening at the boundary between the star's fluid outer layers and its solidifying core that are generating waves or flows that propagate up into the atmosphere, causing the observed turbulence. It's even plausible that this white dwarf is experiencing some form of interaction with its immediate environment, perhaps weakly accreting material from a very faint companion or even from the interstellar medium in a way that is causing localized heating and stirring the atmospheric gas. Whatever the cause, this surprisingly active atmosphere is a reminder that even the seemingly simple outer shells of white dwarfs can harbor complex and unexplained physics. Our journey through the mysterious signals from white dwarfs brings us to our final, and perhaps most frustrating, puzzle, the signal that simply vanished. This isn't about a persistent hum or a repeating burst. It's about a fleeting cosmic whisper that was heard just once and then fell silent, leaving scientists wondering if they had truly detected something extraordinary or if it was merely a cosmic hallucination. The story begins with a specific white dwarf, one that seemed unremarkable until a single observation captured something truly anomalous. The signal itself was unusual in its characteristics, perhaps a very brief, intense flash of light at an unexpected wavelength, or a sudden spike in radio emission that lasted for mere seconds. Whatever its form, its properties didn't fit any known pattern of white dwarf behavior, nor could it be easily attributed to earthly interference or instrumental error. It was, in a word, weird, and it warranted immediate follow-up. Intrigued by this solitary detection, astronomers quickly swung telescopes and detectors back towards this white dwarf, hoping to catch the signal again. They used different instruments, observed at various times, and employed every trick in the book to try and confirm the original finding. Hours turned into days, then weeks and months, but the silence from that white dwarf remained absolute. The signal that had momentarily shone so brightly was nowhere to be found. Repeated, careful observations yielded nothing out of the ordinary. This lack of redetection is what elevates this from a peculiar blip to a full-blown mystery. Was the initial detection genuine? If so, where had the source of that strange signal gone? Scientists have been left to ponder the possibilities behind this disappearing act. One leading explanation is that the event which caused the signal was simply incredibly transient, a one-off cosmic phenomenon that occurred and then ceased. Maybe it was an extremely rare type of stellar flare unlike any we've classified, a sudden instability on the white dwarf's surface that corrected itself almost immediately. Or perhaps it involved a brief interaction with a very small, fast-moving object, like a rogue asteroid or comet, that passed through the white dwarf's immediate vicinity and triggered a momentary burst of energy as it was vaporized or ejected. Another set of hypotheses considers if the source of the signal itself moved or changed in a way that made it undetectable. Could it have been a phenomenon associated with an unseen companion object that has since moved to a different orbital position, or has itself undergone a change making it temporarily invisible? Or could it relate to a very specific arrangement of magnetic fields or plasma that momentarily align to produce a directional beam of radiation which is now pointing away from Earth? Without that crucial second detection, it's incredibly difficult to pinpoint the truth, leaving this vanishing signal as a frustrating yet compelling testament to the unpredictable nature of the cosmos and the many secrets still held within the silent vastness around white dwarfs. So there you have it. We've journeyed through 25 instances where these quiet cosmic embers, white dwarfs, have sent us signals that simply don't fit our current understanding. From strange radio bursts and puzzling X-ray flares to mysterious spectral lines, erratic luminosity changes, and even vanishing signals, these observations paint a picture of stellar remnants far more complex and active than our textbooks initially suggested. Each mystery challenges the established science of white dwarf physics and stellar evolution, pushing the boundaries of what we thought we knew about the end stages of stars like our Sun. They remind us that even in the cosmic graveyard where things are supposed to be winding down, there are still profound secrets waiting to be uncovered. These unresolved puzzles open up a universe of possibilities. Perhaps these signals are hinting at entirely new areas of physics we haven't yet discovered, revealing how matter behaves under the extreme conditions found only in the core of a dead star, or how magnetic fields can act in ways we couldn't predict. They might also be pointing to the existence of exotic celestial objects, perhaps brown dwarfs or rogue planets interacting with white dwarfs in ways we've never witnessed before, or even hypothetical particles influencing stellar behavior. And then, of course, there's the most distant and perhaps wildest possibility. Could any of these signals be the signatures of advanced technology wielded by civilizations far beyond our own? It's a tantalizing thought, one that ignites the imagination while remaining firmly in the realm of speculation, given the host of natural explanations we must first exhaust. Ultimately, these 25 unexplained signals are a powerful testament to the vastness of the unknown that still surrounds us in the cosmos. They are cosmic invitations to remain curious, to ask questions, and to keep exploring with open minds. What do you think about these white dwarf mysteries? Share your theories in the comments below. I'd love to read them. If you found this exploration of cosmic enigmas fascinating, hit that subscribe button so you don't miss our next dive into the unexplained corners of the universe.